if you haven't been handed copies of this page and the next one, you might find it useful to print this out before listening to the rest of the film. These are the standard integrals. You're expected to know them. The first type is having a standard integral. You may need to do some rearrangement to get your integration into the standard form. So you should know how to integrate e to the kx. This is more or less of that form. It's just 12 times a standard integral. So that one's easy to integrate. This one isn't yet in a standard form, but we can do some rearranging. You could divide each term by x, and then you have a sum of terms, each one of which is in a standard form. The next type is where you can spot that you have some function, f of x, and the derivative of that function. You can always use substitution for these. Let u be the function. But sometimes you can use the reverse chain rule without having to actually write in the substitution. The derivative of the bottom line here would have been 6x plus 4. And if you spot that what you have is exactly twice that, what you have is twice an integral where the top line is the derivative of the bottom line. And that's a type where you can write down the answer straight away without using a substitution. Here, the function we have would be x squared plus 1. So if you want to do the substitution, let u equal x squared plus 1. The derivative of that is 2x. Can you spot that what we had was a constant multiple of 2x? So here we're integrating something which you would have got using the chain rule. What I have is the exact derivative of e to the x squared plus 1. And what we wanted was a constant multiple of that. It's only constant multiples where this method works. The next one is a bit harder. I think most people would actually write in the substitution, let u equal x squared plus 3, and use the substitution. But you can still use the shortcut. The derivative of x squared plus 3 is 2x. What we have is half of an expression involving a function and its derivative. So we get half of, and then add 1 to the power and divide by the new power. Here, the derivative of 2x plus a sixth of pi would be 2x. Sorry, I beg your pardon. It would be, the derivative would be 2. So I could write this as 3 lots of twice x squared 2x plus pi over 6. You could use the substitution u equals 2x plus pi over 6 for this. But if you think of it as the chain rule in reverse, this is what you would get if you differentiated the tan of 2x plus pi over 6. The next type is integrating using partial fractions. For this, you express your function in partial fractions and then go back to the beginning and consider each fraction in turn. Here is the integral written in partial fractions. What type are these? Here, you could think of it as I've got a function and its derivative, or a constant multiple of its derivative, or you might think of this as being a standard type which you can integrate straight away. This one is more complicated to put into partial fractions because we have a squared factor in the denominator. When it's written in partial fractions, this is what you get. The first and the third terms you can think of as being the top line is a constant multiple of the derivative of the bottom line. The middle term isn't like that, but that's very close to a standard type. The derivative of x minus 2 would be 1, so you can think of this as being 1 the derivative of x minus 2 to the power minus 2, and we can use the rule of adding 1 to the power and dividing by the new power.